So after completing the solid design principle, we are going to move on the component principle. It is the next step in software architecture design. So what component is? It is the smallest deployable unit. For example, jar files in Java and DLL files in C programming etc. So your application, right? It can consist of many jar files. Oh, why the fuck is pen is not working? Let me check. Yeah. So this application may consist of different jar file, right? So it is a simple. You compiling this jar file to as an independent unit, and at runtime, if you remove this jar file and update the new version of this jar file, you don't have to recompile the whole application. So this is what we are referring as a component. Right. So let's start with the history, how the component concept came into picture in the first. So when programming started, right, from the old era, right, the programmer has to write the code, and they have to give the location of memory address where their program is going to be loaded, or this function is belong to which memory location. So suppose this is a memory location, and your program is loaded at 100 location, and you want to call some function which is defined at 733. So you have to call jump at 733. So this kind of coding you have to do, right? Earlier. So I will tell you how we are mapping it to the component. So in older days, what a programmer has to do, suppose they want to use some library, so they will load that library into their program itself. Like if that library, common library, they have to use it again and again. So what they have to do, they are going to create a common code for it, and they will like put it here, and in their program, instead of writing same thing, they will show that they will say that, hey, from this memory location load this program, that is the common generic program, load this block of code into their program, right? Yeah, it makes sense. So what's happening, so program and all the devices were slow, but the programmer ambitions were getting grow and grow, so they started writing large amounts of code. So what happened, so similarly they have to load more subroutines, right, some method functions, whatever you call, into their program. So their program size started to become large and large, right? It became larger and larger, and it during compiling time, they have to wait several hours, and even like compared more to their exact times, right? And even the program memory size will increase with time, right? Because and if the common subroutine contains extra code, they have to still you are including into your. So obviously this was not a sustainable situation. Programmer has to add more and more function, that is unavoidable. So they have to come up with some approaches. So the solution was relocatable binaries. So what happens? The compiler was change the output of the, like even if you compile some library, from compiler will change its like referencing to some generic, like they will start the referencing from zero for each program. So and wherever you load, you will add that address to that all the referencing that is used in the program. Now the program could tell the loader where to load the function library, right, at runtime. In fact, that loader, so what happens, the loader will accept multiple binaries, and they will load at whatever location they have to load at runtime, and they have to don't have to compile the whole source code again and again. You get the gist? Earlier you have to compile whole source, you have to put the block of code into your source code. Your source code will increase. Now at runtime you are picking and blocking this source of code, compiled source of code, so your compile time get reduced, right? But since since like you are like with increase in subroutines, the loading time got increased, because loader has to re-reference it and update the locations references inside the binaries. So it got increased linker, and then that's how the linker was born to solve this. Linking loader solution was bought to mitigate this problem. So what it does, how it will work, it's uh, uh, this okay. The loader could link the external reference to the external libraries. Again, so this linkers were also too slow. Why? Because there are two parts to it. Linker have to first, when you compile so multiple jar files, let's say DLL files, and your application, and when you compile it, your linker has to link with all the subroutines of the application, right? And now, so what happens? So earlier, what was happening in a loader relocalability? Your loader was working at runtime, so your program loading time was increased, right? Now what linker is doing, they are doing this earlier at compile time only, and then load the whole program into your memory. So this time was reduced, right? So now instead of you have to wait for loading in loading time stage, you are waiting in the linking time, right? So this it was like the programmers is chasing their own tail endlessly, were doomed to endlessly chase their own tail. Because this problem was not solved, but eventually when Murray gave the prediction that chips are going to be faster and their size will be going to reduce, and with recent discoveries and other thing, this time got reduced, the linking time. So still your compiler works this way only. When you compile a code, it will first do linking, and then there is a loading step, loading into loader that loads your program into memory. So yeah, that's how the concept of a component born into the early phases. Now it is used in architecture. Like component, you can call it the single deployment unit, and you can replace it during runtime of application, and it should not impact anything. Replace, I mean, if you want to update your version, of course it should be backward compatible, because otherwise it will not make sense. So we will discuss about the principles later.